start in 5, right? So I'll be back in 2. I'll just do a quick break, bathroom break and come.
Yeah, sure. Yeah.
Yeah, okay.
Hello.
Hi. This
Hi.
is
Yeah. Vinita.
hi.
Yeah.
Thanks for connecting. I think I hear you good. Yeah.
Yeah. Okay. Fine. I think you're good to start. Yeah.
Yeah, I think I just saw this message which Priyank sent. over here as well. Well, firstly, thanks, guys. Thanks for having me on. Um, I didn't really know what to expect when I was given this opportunity to come here. Never done a live stream before, but let's see. Looks like it's a good challenge. I'll try to share some of my experiences overall, and hopefully hopefully there'll be a message where each of you can pick out from this. So yeah, first thanks to the entire IE team. Thank you guys for calling me here. And at the very outset, I hope everyone, you guys are safe and healthy, your loved ones. It's a very difficult time, and let's all try to make the best of what the consequences have given us. Maybe all of us will pull together through the tough times we're living in right now. With that being said, thanks everyone for joining again. I'm Abhinand. I was born in Andhra Pradesh, but I grew up in many cities across India, and eventually I did study in NITK, and I went abroad to do masters. And over the academics which I've done, plus some of the experiences through internships and academic projects, of course, thesis in both your bachelor's and master's, I have begun enjoying approaching any physics-related system with computer programming. You try to model any sort of system, any sort of problem, and use the power available in computation, and try to give it as many applications as possible. So depending on your interest, depending on the flavors of research you're interested in, you can delve into a whole arena of research, and that sort of universe captured me right from the beginning. So today I'd like to talk a little bit about scientific computing, the things which make up this discipline, in my view, in my humble view, and some of the applications which I've done through my projects. Before I start, I'll quickly just go over some of my some elements of my journey through through my studies. I studied mechanical engineering from NITK. I graduated in 2017. So some of the best days you can imagine. College is just a different experience. I think everybody needs to find it in their own, and it just gives you so many different perspectives. It just opens your mind up to a whole different range of ideas. I was also part of some of the teams in college. I was part of Baha, and I was in the Rotaract Club. I was also in DepSoc, and as part of Rotaract, we later on integrated it with Avanti, another cause which I was there for, and we did a lot of good work in all these different facets. But again, the thing which you always remember about college is all your friends and all those experiences. So I took that, and academically I started getting interested in CFD, in computational fluid dynamics, and doing some numerical analysis for different physical systems, and that gradually gave me an interest to pursue aerospace engineering. And I was interested in turbulence, and also the not very much the mathematical part, but I try. When you have to study some physics, you have to put in some genuine effort to understand the mathematics. But I specialized in the aerodynamics track, and I graduated in January of this year. After that, I was able to get a job in this company, Wright Brothers Flight Technologies. It's in the Netherlands, and the idea is to design and you manufacture flight simulators. So as part of this entire process, there's always the requirement of, you can call it a physics engine for the flight simulator. At one particular instant in time, there is a particular orientation and state of the aircraft. You need to solve a particular set of conditions to identify what the updated state is. So it's very interesting, and it gives you a whole different playground uh, to have a lot of ideas in that regard as well. And throughout all these places, I was very lucky to get projects in which I could involve both some computer programming as well as good fundamental physical research. So that was what shaped me, and these are some of the shades which I'll try to bring out in the talk we have for about 15 or 20 minutes. And I'd like any of you guys during any of the slides to just put out any comment or any question or something, a detail which maybe it is was too vague or any sort of thing. And hopefully, I'd like to keep this short. The part about the details, because it depends on how people progress in their own academic career. But please feel free to ask me questions at any point of time. So I'll quickly mention some of the aspects of what I think scientific computing entails. And you always have to start with the mathematical model. You always have to understand, based on your problem, what is the set of equations which you need to solve. Generally, you might have them in the form of partial differential equations. What you need to do is, you realize that if you want to keep solving partial differential equations, you go into so many constraints with regards to the complexity of the issue at stake. So you try to convert it to a set of manageable ordinary differential equations. But why do we do that? Because computers, they love anything straightforward to them. There are many linear algebra algorithms which have been employed for computers. If you can reduce any system ultimately to a matrix vector algebra, computers are very happy handling that. And with the current infrastructure we have, with the current pace at which computers are being developed, you can do very high fidelity simulations, very tasking processes on the hardware, but it won't take you much time. So that's the entire reason. When you have a mathematical model in front of you, you want to essentially reduce it to a set of equations which can be solved with linear algebra, so that you can just give it to a computer, wait for 2 days or however long your simulation might run, and then go ahead with the process. The second aspect is, once you have this base ready with you, how do you approach this physical description of the problem into what a computer might understand through a code? You might write a piece of code, or there'll be a software which does it for you. But there's certain ways in which you might want to identify different aspects of the problem. And one of the terms which I'll talk about is something called as discretization. Essentially, you want to break your complex system into manageable elements. And then at each element, you solve the set of differential equations which you identified for that particular element, and you aim for something known as convergence. In convergence, essentially, you're monitoring a term residual. Over here, you understand that you've solved a particular state and you've attained a certain solution, and you have some truth you are comparing that with, how far away from the truth you are. Essentially, you want to converge, you want your solution by putting the residual as close to zero as possible. Because when you mean that your residual is close to zero, the solution which you computed is as close to the truth as possible. And then now when we have this approach, you can explore a various set of processes. anything which might come to your mind. I'll try to go over some of the projects I have done through my courses, and essentially we will look at an airfoil, which is a system to produce lift at some particular conditions. So we look at some results as to how you can break down a physical process, put it in a computer, and analyze some results. So we'll visualize the flow of air around an airfoil. There was an opportunity I got during my internship to play with satellite data. It was part of the Tropomi mission. I'll share more details later, where you can monitor a piece of the Earth. You sequentially get data from the satellite. You filter out data which is not at all relevant to your particular case. So in my project, it was methane. So I would take out all other parameters measured, and we were able to look at some of the emissions throughout the coast. So if you want to identify a place of high, let's say, oil and gas production, you can identify the process of the air convecting out of those chimneys, and you want to see, hey, around this refinery, what sort of methane concentrations am I looking at? So that is one thing we'll talk about. And lastly, I'd like to tie it up with a new discipline I was introduced to during my master thesis, and it gave me ideas to realize that, yeah, if you want to make an interdisciplinary research, you can find so many nuances. You can find so many ways that you want to tie up to two different streams, and hopefully find some harmony in the between to do a particular project. So we wanted to analyze turbulence in the flow to a bit deeper extent, and amongst the various different the huge ocean of research which goes into turbulence, we had an idea of also including a machine learning approach, and that is what I would end the results with, and hopefully we can tie it up all in the end. So we'll not talk about the mathematics, of course, and yeah, I don't enjoy it myself, but we have to, what I consider it always is a necessary evil, and please don't sue me for that, but that is my opinion on when you have to deal with mathematics. But it's beautiful. It's got wonders of its own. But when I want to approach it, I try to read as much as possible from the literature. You have to look at the research papers, figure out your problem, and I'll try to delve into the second one a bit, so that when we talk about the results, it's much clearer. So before I put up the image for this particular topic, we're talking about an airfoil, which is represented right in the center of the screen. You can see a shape in the exact center, which is hollow. The space around has been divided into multiple elements, and right in the middle we have figured out what is the airfoil boundary, and we are trying to break up the pieces around the airfoil into as small pieces as possible. There are multiple choke points when it comes to this particular decision in your process as well, because you want to get as much information around the flow as possible. So what you can see is wherever the squares are big, the blue mesh, wherever it is big, there the resolution is quite low, because you're taking a bigger piece of space, which if you look at the Cartesian coordinates on the bottom right, you can get your orientation as to how the domain is in this place. So we can see that farther away from the airfoil, we can keep it a bit big, because we're not necessarily so interested far away from the airfoil. But right across the boundary, you can see it's very dense. You probably can't even make these spots in between them, because you want to resolve them to such a good extent that close to the airfoil you can get more behavior. The reasons for that are multitude, and one of the simplest ones is you look closer to the surface, you start to get more friction between the layers of the flow. So you need elements which are much smaller because the variation is so high. If you have them quite big, maybe the variations will keep going and they'll cancel. So discretization is one of the first steps you go when you have a particular system. You're like, okay, what am I analyzing? In this case, it's the airfoil. So you chalk out that boundary, and then you want to go around the boundary and say, where do I need a high resolution? Where do I need a low resolution? And you mesh the area around you. In this case, I've written the term spatial here because if you want to talk about an evolving system, you have an equation which has both a space and a time component. You have to, based on a project, you have to pick your battle. Sometimes you do not want to simulate time at every instant. You just want to take a snapshot of the process at one particular time step, and maybe you just want to look at the spatial orientation around it. So in this case, when you see the elements, they're basically how much the space around the airfoil has been broken up into small elements. And in each of these small elements, we want to solve the set of equations which describe the flow. And the mathematical model for a fluid flow is the Navier-Stokes equations. Whoever has maybe some studying in mechanical, maybe chemical engineering as well, a lot of the places where you have any flow, you know that the Navier-Stokes equation describes them. If you don't, well, I would leave it up to you if you want to go into that universe. But yeah, it's a pretty fascinating set of equations. So in all these elements, we want to solve them. Essentially, when you have the solution at each particular each element, I mentioned the term convergence, where we said that the residual should go as close to zero as possible. But of course, how do you pick that in a simulation? You define, hey, there's a tolerance. So between this particular error limit, if my residual goes as close to zero as possible, then I'm happy. Residual, again, is the difference between the solution you compute at a particular time and what you consider to be the truth. And you want to put them as close to zero as possible. I just put out some lines. The details are not required. But essentially, all these lines are the evolution of the value of the residual. And you'll see as time progresses towards the right in each of these plots, you want them to go as down as possible. Over here, if you may catch the bottom limit of the y-axis in each of the plots, it's -6, 1e -6. So in this case, you pick a tolerance of e raised to -6, and maybe for this particular case, that's a good enough tolerance. This varies hugely based on your application, based on the data which is available to you, based on whatever decision you have to make in order to pick a tolerance. Usually, you will get some help from literature. You will read some papers. You'll find some sources where others might have done an experiment similar to this. But the idea is to evolve all your systems. So basically, all these different lines represent the residual for different partial set of ordinary differential equations. So the residual of all these ODEs, you want them to go to zero as quickly as possible. Now, here is a different branch of computing which might open. Okay, what are the different models in which the tolerance can be even higher and you can go even more in resolution as well? That's a whole different field over there too. But that's the idea. You break it up into small pieces, and in each element, you solve the same equation over and over and over again, iteratively, until your residual goes below a certain threshold. And you're like, okay, now I'm happy. Now, maybe the variation is now 10 raised to -6. I'm happy. Now I'll go ahead and probably look at what the flow around me has done. This is the modeling which this is the generic description of what I can say as modeling to any physical process. Now with this methodology, I'm going to try to go into a bit of detail in a couple of applications, and hopefully, if anything is vague, again at this point of time, I encourage anyone, if you want to shoot a question or have a comment at any time, please feel free. So the airfoil which we just discretized, which we just made elements all around it, and we gave it some conditions, all these different models, all these different tolerance values, etc. Now you essentially want to see what the results are. Two parameters which we are seeing in the left and the right, and then the right plots. We are monitoring the pressure. I should stay on the left side, and we're monitoring how fast the flow is, the Mach number on the right plot. You can see again the chunk right in the middle. That is that is blocked out. So that is where the airfoil is. That represents the region of the airfoil. In our case, the flow is going from left to right. So if you can imagine particles going across the screen, when we are looking at it, so from where, let's say, the color bar is, from the color bar, the flow is impinging on the airfoil, it's coming through, and then you have the region after the airfoil, and you have regions above it and below it. So the upper surface, the region above the upper surface, and the region below the lower surface. So you have these regions, and you essentially, based on the discretization, you want to identify the solution at each of these points. All these points and all these elements that you've created, at all those places, now that you've solved your equations, at each element, now you have a solution. So you display solution in different ways. In this case, so we're looking at contour plots. So we are looking at a region, and whatever the color in that particular region shows, it represents a particular value of that physical quantity. Now, when we look at an airfoil like this, and we want to say, all right, let's try to understand the flow which is happening here. And there are two terms which always come up when it comes to an airfoil. There's an upper surface and there's a lower surface. What you see here is, on the left side, we have the pressure. Above the airfoil, you see that the gradient shows that it's pretty low over there. The pressure is pretty low, and it's a bit higher on the lower side. If you well, it's I should probably not say Bernoulli's equation 1-to-1 for this case, but just think about it. So if you have a high pressure, there's going to be a low velocity there, and vice versa. So above the airfoil, on the left, we see above the airfoil, the pressure is pretty low, and that corresponds to a pretty high speed on the right. So there's a red region right above the airfoil on the Mach number to the right of the screen. Similarly, on the bottom, so you have these two terms called as the suction side and the pressure side for each of the surfaces of the airfoil, and this can give you a good idea. Okay, now since there is a pressure gradient across the airfoil from higher in the lower surface and lower pressure in the upper surface, there's a force which lifts it. And when you look at the airfoil now you want to calculate what is the lift which it can produce, what is the drag it faces because of its orientation, because of the flow conditions, etc. And with this methodology now, and this sort of analysis based on the results, you can vary whatever you want. Perhaps you want to increase the speed of the flow. Perhaps you want to reorient the airfoil to a different angle of attack. Any physical process now that you want to analyze, you have a methodology, and it comes down to over here. We're looking at the pressure and the Mach number. A couple of things again. So you see that at the tip of the airfoil, the left tip, where it's beginning, you see that it has very high pressure, and the velocity is almost zero over there. That's called the stagnation point over there. So you can visualize all these features which you might come across during the mathematical model, during some research you read through a paper. So if you're doing a project and somebody's written a paper, and you see these results, and now you want to verify these sort of results on your own. So this was an aerodynamics related example. And I mentioned that during my internship, we had the opportunity of looking at methane emissions. The region we chose was the Gulf of Mexico. So what you're looking here is the map of Mexico, and the tools we used for this particular project was in Python. So before, I showed you an application where we do it from a solver. So we have answers available. Other solvers for various different processes are made by people who are vastly experienced. You have so many finite element solvers, etc. So you get the idea over there. Now we have a different tool, but essentially again the idea is the same. Over here, what are you looking at? Imagine there's a chimney which is putting out some gas, and the air is convecting around it. So therefore, the particles will diffuse around the area of the refinery. The concentration of the gas will of course be higher, As you start going away from the refinery, the values keep getting lower. So you have different tools in different from different avenues you can get throughout computer development as well. So again, this is a Python example, and there's a very good library which is used here. It's called Shapely. So I would encourage anyone who would have anything to do with maps and let's say any other application apart from environmental analysis on maps. The great thing which people, the ingenuity which people come through, they make tools and everybody can just use it for a particular time. For example, Shapely, there is a simple function which allows you to check if a pixel. So here, how we break up elements, there we had elements around the airfoil all across the flow. Here we just put pixels. So if you have a resolution of the satellite, you can figure out what the dimensions of the pixels are, etc. So maybe the satellite, which was here, that was an advancement in the hardware. They could narrow down to a 7 kilometer times 7 kilometer pixel, which is very unprecedentedly high resolution based on what satellites can do. So the idea is the same again. You break them up into pixels, and you have one equation which defines it. So that there might be a simple convection equation based on how much rate of the emission is going through, what is the direction of the wind. So let's say there's some rate of maybe 10 tons per hour or something like that, and it's going northwest at a particular temperature and time of the day. So you have an equation which describes that. Solve it on every pixel and figure out what the rate of emission is. So by again visualizing, let's say, the coast, you see that there are some high concentration points across the coast. And as I said, that in Shapely, you have a very good condition called is land. The pixel, if you just ask it if it's on land or on sea, you can figure out, it'll give you a condition true or false. And essentially, Python has even more tools which you can add to that. Now that you have identified all the pixels which are not on land, so you don't have to waste your computer's effort to compute the equation for those particular pixels. So you can just mask that array. So anybody, again, with some Python experience, you want to integrate it with other tools. People, when they started experiencing different applications through computers, so many different tools open up, so many different ideas you can just capture for your particular application. Figure out what are the things available to you, what are the things you need to do, and then just try to get a harmony in between. So over here, we found these high concentrations, and our focus was anyway to zoom in on the coast. You see the peninsula where it's arching towards the bottom of the plot. So we zoomed in over there. We had a study which went around some of the refineries there, and they had some data to verify with. So we, with the satellite, could bring out emissions like this and put it across their data, and we had a good match over here. So the same approach, now we saw some environmental applications. We see what we can do with any of these other applications. And then the last sort of avenue which I want to bring forward is something which is very dear to me, because I think once anybody okay, maybe not speak for everyone, but someone who puts effort into a particular project, especially a thesis where something depends on it and you have to keep going for it. When you have a proof of concept, when you try an approach of your own and it succeeds even to a basic rudimentary level, that gives you a lot of satisfaction. So essentially, in Turbulence, when you start reading, you find so many different people who have done so many different things, and then you find that some of them do not work in every other case because the equations we are tackling, ultimately the Navier-Stokes equations, they are notoriously tough to solve. Sometimes, if you have the same condition and you run the simulation for the exact same set of things, you run it 2 times, you will get completely different results, and you'll be scratching your head. Wait, I just thought it was supposed to be repeatable again. So it depends on the complexity of the problem, how much people have, how many different layers of complexity are there, how have people studied too much in the mathematics, have people studied if there is a certain set of mathematics which can be reproducible, because again, what's the goal? Computers love something which is predictable. You just give them a simple matrix operation, computers are just happy to do it. So based on the mathematics of your the stage of the mathematics in your turbulence, how much can you model? How much do you want to model? Can you get away with some stuff? Do you need to do some stuff? So essentially, we had a system of equations in the finite element method. It is one of the ways in which you can break up your domain. Part one of the discretization schemes is finite element method. And in that, when you're solving the Navier-Stokes equations, you get something known as interaction terms. So when there is a nonlinear interaction which is happening, that is the most difficult thing to model, because if you look at any set of partial differential equations, anybody can tell you that when you have a nonlinear interaction, you probably need a lot more information to proceed with your answer. So we try to make the neural network learn interaction terms close to the wall. So if there is a flow which is going between, let's say, in a pipe, and if you take a cross section of it, there's a top surface and the bottom surface. So close to the walls, there'll be some turbulence interactions. There'll be a flow in the middle of the pipe, which is more uniform, but of course there are some interactions there as well. So you try to have a resolved flow, which is present to a certain extent throughout the domain, and then you have something called as an unresolved component. These are the terms which you want to let a neural network learn, because you are banking on a different line of research which was proven that if you provide nonlinear interaction to a neural network, you don't know how it learns it, but it does it somehow, apparently, based on the training data you give it. And then that's where your subjectivity comes into that as well. And then once you have a subjectivity, objectively form constraints based on the literature before you, read some papers, what have people done over there. So in the finite element method, what we try to do is to learn these interaction terms. And up until a certain extent, these neural networks would have to be given some additional constraints to be successful. But my idea was to add noise to the training data. So we added noise in two ways. One was a signal which was uniform, so it was a white noise signal, and I also modeled a Gaussian noise signal to be added to the training data. Now again, since there are many elements here, you have the neural network part, and you're trying to approach it with enriching it with noise, but then it is juxtaposed with the physical part. Now you have an entire domain. You have training data, let's say, of the pipe again, somewhere in the middle of the pipe and somewhere close to either walls. Which training data do you want to corrupt with noise? Do you have to corrupt the entire of the domain? Or in this case, since you read the math and then you understand that, okay, close to the walls, the behavior is much more unpredictable. It is much more difficult to understand that. You're like, okay, I'm going to choose only the data near the walls, and I'm going to target that with noise. Hopefully, I enhance its signal, and the neural network can physically give it more weightage, because somebody who's probably interested in neural networks and probably has done something, they might know that you can add weights to the nodes for the neural network as well. Fine, that's a great suggestion too. That's something which can be delved into. But you have some insights which come from the physics. When you know the physics, when you know the math, you have some sort of insight. And then you do I need to do a one-to-one interaction? Do I need to do a many-to-one interaction? All these decisions, you get the freedom to make them. And essentially, again, you have to pick your battles. What are the ideas which are already proven in literature? What are something which I can just pick? And what are places that I can meddle with a bit? Maybe I'll fail, but that's fine. That's part of the thing anyway. So half the models I trained would blow up in the end, because simple reason, maybe you corrupted too much with noise. Maybe you didn't corrupt enough with noise. So by doing different combinations, essentially we added two sources, a uniform signal and then a Gaussian filter. And what we found was very heartening, because over here you see many lines, but let's go through it one by one. Let's go to the legend, and that's the sequence we'll follow. The continuous black line which you see is, let's say, the ground truth. It's a higher fidelity simulation. Here it's the direct numerical simulation. So anybody who's probably fluid dynamics interested and know something over here. So it's a DNS solution which represents the truth for this, at least for the context of this particular problem. That is true. So we want to go to it. You see, it's pretty smooth. So it is continuous or quasi-continuous, because the resolution is much more than your model. So you can consider it to be almost continuous. There are there is a steady and a sequential growth of the solution. But you have a model which takes 8 elements in your domain. So on the x-axis, you see the spatial component. They're all non-dimensionalized, by the way. So you have a wall, your left wall at x equal to 0. You have a right wall at x equal to 1. And at both those points, your flow should come to 0, because the element which is just attached to the wall, of course, is not moving. That is, of course, one of the conditions. You can have some slip conditions as well, but again, that's different physics and etc. Here you have, that is essentially the two constraints to your flow, and you have a flow which is progressing through the bulk of the domain, and you have a smooth curve. But what you're doing is you're sampling this domain in just 8 elements. So the other lines which you see, you'll notice that they have certain symbols, and they show at what places are you sampling the essentially at what place are you sampling the solution, because you're only solving the system for those 8 or 9 points. Here there are 8 elements, so there's 9 points throughout the domain, and you have the speed, which is the velocity, which is shown in the direction of the flow. So if the flow is going in the x-axis, you're measuring what is the speed of the element away from near or away from the wall. So the x-axis 0 shows the left wall, 1 shows the right wall, and how much in the direction of the flow is the particle moving. Now the second line is basically a projection of this true solution onto the 8 elements mesh. So we call it a P. So, and L2 is the scheme of the projection, let's say. So we have the projection of the true solution that we want to match. That is essentially what we want to do. So we have a box, and we want to hit that box as much as possible throughout the domain. Previously, the work which was done, which is shown in the red line, and that's a different symbol you see, that is what we are competing with. That is what we want to do better from. So the neural network which we trained before, there was no noise added to that system. So it would learn on its own. It's good enough. It's a good enough system on its own again. So it has its own merits, but it would, at the end, to be stable, to provide stability in the long term, keep producing accuracy as well, you would have to provide some limits to its predictions. A very brief idea. So if you have the neural networks, if you want to model it from a -3 sigma to a +3 sigma, a big curve, you are limiting any predictions outside that limit back inside that limit. That's a very rough idea of what I said. Essentially, any outlier data, you're just treating them, and you don't want to put them in your in your simulation. So if there's any outlandish prediction by the neural network, you squeeze it back in to your particular bandwidth of what you consider as good. So that is the red one, is what we're comparing with. And there's a very interesting phenomenon which happens here. If you look at the 2 points in between 0.6 and 0.8 of the x, so you see there are, of course, the 2 black boxes. That's the projection. That's the solution we want to match. And over there, first of all, you see that the solution is continuously, as it goes towards the right, it is increasing. Of course, near the right wall, it has to sharply descend because it's going to 0. But you see that it's sequentially going up. So you see the black boxes as well. There is a steady positive slope between 0.6 and 0.8 of the x-axis. And you see that the previous solution, because you wanted to make it stable, you gave it some limits, but essentially it gave you a solution where it dipped over there. And if you want to look at it, you might scratch your head and be like, that sort of does not make sense, because, I mean, why would suddenly a point there have to go down? So the point after 0.6 closer to, I'd say, I don't know, 0.75 or something, that guy should be higher than the one in maybe 0.62, if you want to call it, or something like that. And maybe one of the reasons for that is perhaps limiting, maybe, of course, if it's giving outlandish predictions, perhaps the network is not stable in the first place, but you are limiting that neural network in order to give a stable solution. Good for you to a certain extent. So maybe it's going on. But then now the investigation comes as to, okay, now let me target some data during my training and give it some noise. It could be the two noise signals, as I told you before. So the abbreviations which you see, the G before the A and N represents a Gaussian signal to the of the noise, and the W represents a white noise signal. The parameters inside are based on the simulation, so there might be some extra details. But again, you have lines which with symbols of the crosses. So again, the idea in the picture is to have those boxes and keep hitting them with your crosses as much as possible. And this was one of the first results I saw as well. And I saw that, hey, actually being a bit smart with the noise gave me a solution which was actually physical. And the lambda equal to 0 parameter which you see there, that's basically the limiting parameter. The idea of when I was saying when there's an outlandish prediction, do you want to squeeze it in? And when it says 0, it basically means that you're not giving any limiting parameter to the neural network. You're just allowing it to freely flow and give all the predictions possible. The red, again, I would remind. So if the parameter lambda, so in the red, the lambda would be a 3. It's basically 3 sigma. So the lambda would be a 3 in the red, but it's 0 in the lines below that. And when you keep going across, then you see a line like the violet one, where it's the Gaussian one, where you give the scaling parameter of 10, k equals 10. And you're like, oh no, maybe I went too far. Maybe the noise disrupted a behavior to a greater extent than you wanted it to be. So between in all these realities which juxtapose, there's the mathematics which defines the flow, and then there is, after you have the mathematics, you have a numerical approach to it. You use the finite element over here. There are so many verticals which drop down from finite element as well. But then you pick one particular nonlinear interaction term or a set of nonlinear interaction terms and decide, okay, this is something maybe I want the neural network to learn. And now you're like, okay, now there's a domain here. My neural network is not always performing as I want it to be. And now I have some data which I know for sure, because it's closer to the wall, because the particles close to 0 and close to 1, they face more friction because of the wall being closer. Maybe I can give a shot in not corrupting the data, basically enhancing the data with an additional noise. So what if to imagine it, let's say if your signal has a bandwidth of 1.5 units, something, maybe give it noise so that the neural network gets maybe 2.5 worth of the data. So even though it's learning the entire domain, you're giving it a bit more of a jolt in the walls. You're like, okay, let's see what can be done here, and then you employ that. Why do you want to do that? Because you want to convert them to a set of ordinary differential equations which a computer loves to solve. So there are so many constraints. There's so many elements which go into it, and then essentially what you have to do is pick your battles. And that's where I think the overall culmination of what I would like to say, the basic motivation which I would like to give here is that you can attempt to model any system you think of. Essentially, you need to compartmentalize it. The entire problem, you need to break it down into all the elements which make up that particular problem. The first thing you need to do is to do some research. You have to do some literature study. You have to go through people who have done different things, different ideas. Have a feel. Just have a feel of the lay of the land. See what's there around, and identify places where, okay, this much I can trust this work. I'm just going away from that. And if you're going to tackle any particular problem which is very pointed, which has a very specific question, you will subconsciously we'll make so many decisions, and we'll carry over so many ideas. For example, the mathematics. If you want to put a cynical argument to a study, you can take off all the roots of the study. But again, so you have to look at the battles which you want to pick. You want to see, okay, I can trust the mathematics, I can trust the numerical modeling, I can trust my computer to do what I tell it to be. So, and then I have some layers deeper than that, one layer deeper than that, and maybe you have the overall turbulence model which you want to maybe meddle with. And then there are many facets to it. Okay, now a new machine learning approach opened up. Oh, maybe I can go there and now add a noise over there. So there's an illustration. I didn't have the time to put it up, but it's basically when the level of the study keeps growing in any particular field. First you form a cocoon, you find many different ideas. Then as we come to high school, we know a lot more about a lot many things. Then when we go to college, we know a lot many more. But essentially when we keep going forward, you're prodding one particular area, but you have the context of all the bubble which you just created for yourself. And that essentially is the second step. Trust some ideas, borrow them. There's nothing wrong in carrying forward a work before that, because somebody has put their blood, sweat, and tears in that. You can trust it if it has passed a particular review. And then you need to put in some thought. All right, there are so many facets over here. Maybe I'll pick one or two. Maybe I'll see what I can do with it. And then you have to create a methodology for that. This, I hope some of the IT comp science people over here will agree with me on this statement. Look, it's always essentially garbage in, garbage out. If you tell your computer to do some nonsense, it's not going to magically solve the system for you. If you see an error message on your screen, it's probably you who has caused that error message. There's no way, because the syntax is complete, there is no way that at one particular time C++ and its class definition will not accept the semicolon. You define a class, you have to put a semicolon, otherwise it won't take over. So if there is any error you see, and this goes with every other software as well. If anybody who's interested in writing in LaTeX, they'll understand. If you have a compilation error in LaTeX, it's one of the worst. It's one of the worst to see, because it's a huge document. You have no idea where you missed a comma or a dollar sign or whatever, and it just freaks you out. But essentially, what you tell a computer to do, it'll always give back to you. It loves things which are predictable, and it's up to you to take an unpredictable issue, break it down into elements you can trust, identify elements that you can play around with, and try to make them as predictable as possible. And the way, as I said, computers love matrix calculations. So just break them up into linear algebra systems, and then you're good to go. One thing which I'd probably like to show here, this illustration. So just to give an example of how you want to keep track of so much work here. Essentially, I said you cannot blame the computer if it has thrown an error at you. It's essentially your fault. So always have good documentation. Make something which you can always go back and see what it is. For a simple system, something like this, make a simple flow chart. Understand, hey, which system can give command to what? Can I interchange between any particular thing? For example, should there be a bridge in this particular illustration from stabilize to run? Essentially, no. What if you're thinking of some let's say the orientation of a particular body, in space and time, and you're asking it to stabilize. Maybe something went wrong, and then so you froze the simulation. You're like, okay, now something happened. I need to fix it. So essentially, you froze it, and you did some diagnostics. You're like, stabilize it, and then you have to make a decision here. Can I? Somebody who's interested in programming, since you can already think of all the switch cases and the if conditions which come over here. Should there be some connectivity from stabilize to run? And then you need to make a decision. No, because you just want to go back to freeze, because the stabilize in a physical sense is a subset of a frozen state. So you need to keep track of your sequences, and clear and simple diagrams always help. There is nothing wrong in even just taking out a piece of paper, just make a pen, and simple block diagrams always help. So again, don't blame your computer for any errors which come up. And finally, just treat a computer like a friend, because you need to invest in good hardware. This is something I would like to say in general, because I'm not very knowledgeable in this front as well. This is, according to me, this is the third element which would increase anyone's productivity in this particular field. When you understand some of the hardware which goes into some of the infrastructure which goes into computers, some of the people are very interested in mid-level or even low-level machine-level programming as well, and that is remarkable. That is the amount of possibilities that opens up, and the new dimensions which go from here. We have quantum computing coming up, and some of us might have heard, some of us might not even know what the hardware is all about. So when you have a system in which you want to perform your simulations, invest in good hardware and essentially set it up to your liking. 100 people will tell you 100 different things as to, oh, this graphics card and this tweaks and this and that. But essentially, you need to identify your need. You need to fix your computer for what job you want to do, and just have a process where you can always iterate, where you can come back to a point. You can think of a condition. You can decide for yourself: have I achieved that? Have I achieved that condition for that particular cycle of events? And can I proceed to the next cycle of events? Hopefully this is a sort of tied up message which could be applied to many different avenues. But that is my my prime message for all, is that if you have any system in front of you, there's a very good chance that if you think about it and if you break it down into some things you can trust and some things you want to identify as possible areas of research, it is always up for a computer. A computer is always up for the challenge of doing a 2 or even a 3-month simulation. Who knows? So yeah, that's it. Thank you guys again for your time, and I would love if there were any questions from people, and hopefully some of the ideas were clear. But if anybody wants me to revisit a slide or has any questions about it, I'm eager to look at what's here. Hi, Kaustav. Thanks for tuning in, first of all. So Kaustav asks us, hey, okay, let's do this. I know there's questions here. So okay, Suman's here as well. So maybe let's go a question by question, and then I'll give a cue, and then you guys can type in more so that we don't get lost with so many questions. So let's keep it here for now. Yeah, so I think both the questions could be intertwined. Costa basically talks about the motivation to go into CFD, and Sumant is also, I think, delving a bit into I think bit of the technicalities into the modeling. But essentially, yes. So you need to identify, first of all, that you're okay with looking at a computer screen for lengthy portions of time. And there'll be, for example, the worst sort of error which I look forward to is if you have a pointer leaking in C++, you get a segmentation fault. It's a useless error message. You won't get a single piece of information after that. Or maybe I'm not knowledgeable enough till now to deal with segmentation faults much in a much more productive way. But the point is, you need to be up for the challenge of facing a computer screen for a long time. Essentially, that is it. And you need to understand if the mathematics makes sense to you. Because if you want to solve, if you want to take up CFD, you need to have a good enough engagement with the mathematics. And I would say a bit more for the physics, but I mean, they're all intertwined again. We are discretizing science as we want into different fields, but they're all intertwined towards the end. For CFD, I would say, if anyone, let's say a good litmus test for someone who wants to do CFD or just programming with the help of many different tools in the applications I showed you. One was a solver, one was a scripting language like Python. MATLAB, for example, is very good for all the scientific community. And the third, the thesis plots which I showed you about the machine learning, it was in C++. So you need to have some engagement with the mathematics, the physics, as well as the computer, and you need to have some courage to just keep debugging for ends on end, for days on end. But essentially, there'll be light at the end of the tunnel. So yeah, hopefully that goes. So yeah, I hope I answered that question over here. So maybe another one of you guys can shoot. Yeah, but maybe I can add a bit more to what Sumant asked about the reliability to different scenarios. Yeah, I mean, you got to be ready for failure. That's it. That's the long and short of it. You try to best model a scenario. If the solution does not converge, it does not converge. There's nothing you can do about it. And then you need to revisit some things. Maybe some model parameters. Because, I mean, let's face it, you're modeling a reality. So there is an implicit error already. So what you are hoping for is a computer to be fast enough to reduce any precision errors. So there's a play of a modeling error and a precision error as well. So you need to play around with those as well. Usually you can manage most errors. That shouldn't be a problem. Hi, Manan has a question. Yeah, so someone asked us if the machine learning was a bit. Actually, I found it a bit tough to start with because the jargon was a bit too much for me after a while. There was a lot of concepts which I kept reading, and I thought this then I started looking at the terms in a very literal sense, batch size and just epochs and stuff like that. So it's a great topic, but I think one thing which I try to do with new tools is to create proofs of concept. So any new tool I want to learn, any new let's say a library in Python, for example, just make a small code, try to do it. Essentially, the machine learning in my thesis was done from Python, and I transformed that into the appropriate matrices for the C++ solver. So again, so just make a proof of concept in any. I would like to answer this machine learning aspect in a more general term, that if you want to learn something new, just make out a cycle of events which make sense for the project. So there is some input conditions, some sort of methodology, and it goes back into some other system to give you an output. So make a small cycle and do a proof of concept. That always helps. It gives you confidence as well, and just gives you motivation to keep going from there. So yeah, hopefully that question I answered. Hi, Vinita. Oh, yeah, nice question. I don't know. First of all, okay, I don't know what you mean by explode any fields, because the thing is, if you take any project towards the end, there is again the juxtaposition of so many fields which go into it, and at any particular project, at any particular juncture, you can diverge in a way which is completely unique to your thought. So you can suddenly think of the mathematics and say, okay, no, I don't want to think of, let's say, the end game of all turbulence and these sort of things. There's something in the mathematics to do, for example. So for me, the field of interest began from a liking for physics, and essentially then I realized, okay, computer programming is not so bad if you can get used to it. And it does get tasking a while though, but so these two elements slowly they started motivating me. I took some courses accordingly, some electives in NITK as well. And with regards to the mathematics, because I still struggle with that. In the odd sem, I forgot the name of the professor, but you get a linear algebra course in odd sem in NITK. Yeah, somebody maybe, if you guys know, then can put it up for the rest of the people on the chat box who the professor is. Oh man, it was a brilliant course. I should remember it. But yeah, so you need to pick ideas which make sense to you, and something which you can entertain to a certain level in your brain, because it might get overwhelming, but some effort needs to go into any field to master. So for me, it was again a liking for physics, and programming sort of came in. So you can simulate any sort of system. Yeah. So yeah, that's how I ended up in CFD and numerical modeling. Let's see. I think I have a couple of additional slides. I'm just seeing if maybe while we wait, I could probably go ahead with another illustration. So once again, when you have, let's say, a proof of concept over here, I explained for the airfoil, you had the chain of events coming in from the numerical analysis, the mathematics, which needs to be considered. Then you break it up into discretization. I showed you the mesh close to the airfoil. It was pretty dense. Away from it, it was pretty sparse. And then you apply different models and go ahead with it. There are interesting phenomena where if you keep playing around now with the parameters, now that you have your chain, you have your proof of concept, now you're confident to do a couple of things because you have the verification already. You are confident that it will work as you expect it to work, at least to a certain extent. I mean, it can always fail. That's the first thing. Any simulation, it can fail at the first instant, and you need to be ready to look at it and like, oh my God, what's happening here? But over here, the concept of a boundary layer for people who are interested in fluid dynamics, you look at it and you want to keep increasing the resolution close to the wall as much as possible. So there's the white chunk which has been taken off, which is the airfoil, of course, just above the upper surface and below the lower surface, around the boundary of the airfoil. You want to keep increasing the resolution as much as possible, keep going as much as possible. So again, you need to pick your battles once again, because there's a lot of time. It will, if you have too many elements around the airfoil, somebody might say, okay, let's just fill it up with as small elements as possible. But if you wait for a way longer time, or sometimes since you've taken such a small snapshot of space, the length of the element is so small, maybe the variation is so bad that it's always unstable, and you can do many things. But this is another model, let's say, because we increase the resolution close to the boundary layer, and you can see apart in the upper surface of the airfoil, after there's the low pressure gradient right there, you see a small bubble which forms there. And people who might know that variation over the airfoil based on the orientation can imagine that when you keep increasing now for different scenarios, because this is still, let's say, a decent enough case where the airfoil is probably, I think in this case, it's 4 or 5 degrees from the horizontal. But let's say an aircraft, right? An aircraft, sometimes it's pitching up with a greater angle of attack, or sometimes a fighter jet, which is doing flip sides on itself. So all that matters. So based on your based on the amount of time you have for a project, for example, if this is a 1 week assignment, of course you do not have time to make such a big test matrix and do all of that. But if it's a thesis, now you have much more freedom. What else can you do? So the play with different parameters does that. And essentially, as I said, for many different models, you want to see how much lift the airfoil produces. So how much force is there in the positive y direction, how much lift is there, and how much drag is there in the x direction. So basically, how much it is it impedes the flow of the flow over the airfoil. And you can try different models. And here's a brief table of the lift and drag. So you can do different models, see, okay, which is my best combination where I have the highest lift, lowest drag, those sort of things. So if you have the proof of concept, now you have the freedom to do whatever you want. So hopefully this again can tie up to some of the other things I said, that any system you have, after a certain point, you can you can get away with many things. So once you start seeing the results, you will feel happy. So I hope that motivates you guys enough to do that. Hi, Pragyan. Yeah. So I mean, so you asked a question about solvers, which I believe is a very good entrance to any different field, and that's what the second point of the first parallel. That's what I want to say over here. You have ideas which some work which people have done before, and a solver is really great at that for you. It has you can trust it for the mathematics, you can trust it to the physics to a certain extent based on how much data you give it for, let's say, modeling the viscosity, for example, those sort of how much you can enrich a solver. And a solver gives you great plotting tools. You can make contours like this, etc. So again, I always approach it in an iteration. So if, let's say, you want to start with answers again, look at let's say some YouTube video and figure out a problem which, first of all, you enjoy thinking of the mathematics and the physics. Maybe you can take an airfoil. Airfoil is one of the classic. You can make a cylinder ANSYS simulation as well. You can do the one Carmen Street behind it if you're interested in that. But that's the thing. Think of a project which makes sense to you and figure out a small loop, a small proof of concept which you absolutely need to nail to be happy with the process. So again, with ANSYS, it can be with a piece of code. Again, it can be with a scripting. As I said, if you're making a script in Python and you need to do some process, always, I would say, have an idea as to all the steps which are there, and exist one level higher, I guess, for the overall message. But once you have this proof of concept, let's say in ANSYS, figure out a problem, do a small thing, and once you have a confidence with the tools, okay, how do I mesh? How do I discretize? How do I set a particular constant? How do I change, I don't know, the dimension of the airfoil randomly? I'm putting it at 5 degrees. I suddenly want to put it at 15 degrees. So all those sort of things, get confident in that. And essentially, it's a snowball effect. It'll keep rolling, and you will keep getting more confident in that. So start with YouTube videos, always helpful. And in courses, you can do a lot in college as well. Just keep a lookout for the right courses in different departments as well, right? And I would strongly suggest anyone who does not like core programming, especially C++, for example, because I really do believe that if for physics simulations, a good knowledge of C++ takes you certain areas. So I would strongly suggest a lot of people to at least interact with coding to a certain extent. It gets very difficult after a point of time. Even the most seasoned of programmers, you might talk to many IT and com science people, and the kind of problems they tackle as well. For example, somebody could make this is actually an example one of my friends had told me about. He made a project where he created basically a parking lot, a ticketing system for a parking lot. It's a very real life problem. You can solve it with code. Again, break it up into multiple pieces. There'll be like a ticket machine. There'll be like a gate. There would be, a place to park, those sort of things. So anyone in these, in the non-IT com science people, I would suggest, apart from the solvers, just a bit, Python is a good step. Then try to go a bit more into C++ too. Iswant again. About turbulence modeling. Yeah, see, so the last part of your question again, where you mentioned a couple of models, I would say again, for this particular question, it's too far. So it's again on RANS and LES, and with DNS, of course, there is no modeling in a sense, but you have precision error there as well. So the models come at the end of the story. It first, when you want to look at the mathematical description of any turbulent flow, you want to see how you are what is the amount of the solution which you can trust in that domain. So in RANS, the name of the models which you put out in RANS, which is the Reynolds averaged Navier-Stokes. So the averaged part makes it that for a length of period in time, you have a system which has been averaged. So that's the first step you might probably go into turbulence. But then if you go to something like an LES, you just take a snapshot in one particular time, but you don't average it. You resolve it, and there are nonlinear interactions on the unresolved scale on the very low on the very low wavelength, very I should say high frequency. Yeah, the very high frequency modes of the solution which you cannot model, and they're called the unresolved. So when you have in this particular specific to this question in response to turbulence, first look at the set of mathematical equations which have been converted to ODEs. What is the logic which has gone over there? The models just a play on that mathematics over there. So when you have an average solution, the models which you said like K epsilon, K omega, they're just different ways of expressing the physics. So, the interaction between the dissipation and the energy, the interaction between viscosity and all of that. So people then come up with different physical models. But again, that's the later part of the story. When you talk about turbulence, again, keep this loop always in mind for every small topic which might come up in the research. Look at the mathematics. Look at the way in which they're trying to describe the physics. That would give you, let's say, the gist, the trunk of the tree. And then all these names of the models which you say, they're just branches. People, different thoughts with different empirical data and those sort of things. So yeah, mathematics. I can't give a better answer than that. Let's see. Yeah, but I'm curious if there are any electronics people here, civil engineering people, metallurgy people, of course, comp science IT guys. Once there's the solver, sorry, once there's the code which comes to you, you can do many other problems. But when you have technical study in your college, I'm very curious if people have turned up from electronics and metallurgy, because there are many systems which can be simulated as well. Maybe a blast furnace. Somebody is interested in steel production, and you want to just model the temperature evolution inside a blast furnace. You can do it with some code. So if any guys who wants to give me a different perspective as well, let's say, because electronics, let's say, is one subject which I could never completely appreciate because I was quite bad at that. So I'm curious if some other branches apart from let's say mechanical or aerospace enthusiasts have turned up here. Or else I think Priyank has put out, I think, sort of a last call for questions. Maybe we can wait 5 or 10 minutes more, and then yeah. Yeah. I guess we don't have questions, and yeah, I mean, thanks a lot, guys, again, just for making time. I hope it was somewhat understandable. In at least you could appreciate some of the nuance. That's what I was hoping for. Maybe it does motivate any of you in any discipline to just pick up a system and try to simulate it, because we have the means. Computers are only getting stronger by the day, and we can make the best utilization of that based on the skills. So yeah, thanks again for the invite. And maybe if Vinita, I think if you're in the chat, maybe you can take over. Or I don't know if Priyank is there on the chat as well. Sorry, in the stream.